One small little thing that I want to do before we move on to the end of this chapter is to look at what's called isomerization or isomerization. Yeah, the word iso means equal, and isomerization in chemistry is a process by which we take the same number of atoms and create different structural molecules. Okay, so the way in which you know you have a different molecule is by applying the IUPAC rules for naming compounds, organic compounds, and if you get a new name, then you have a new compound. So isomerization is taking a group of atoms and arranging them into different structural formulas so that you get a new organic hydrocarbon. So before we begin, there's three things that I would ask you just to call to mind. And first of all, know the functional groups that we already have studied. So the alkanes, the alkenes, and the alkynes. So the alkanes, as we already know, is a C single bond C. The alkenes have a double bond between two carbons somewhere, and the alkynes have a triple bond between two carbons. So they're the only functional groups that we've studied at the moment. We will next year move on and we look at the alcohols, the aldehydes, the ketones, the carboxylic acids, and the esters, but that's for 6th year. For the moment, we're just happy with these three. Know the arrangement of bonds around the carbon atoms. So by moving the position of the double bond, do I get a new compound? Does it become, for example, pent-1-ene, pent-2-ene, etc.? Yeah. So by moving the double bond around the place, do I understand how that affects the name of the compound? And lastly, then, to understand something which I haven't yet spoken about, but we will before we finish this chapter, and that is the shorter the hydrocarbon, the lower its boiling point. But not only the shorter the hydrocarbon, the more branches that hydrocarbon has, the lower its boiling point. So therefore, there is a method in chemistry by which we can take long, pretty useless hydrocarbon molecules, reduce the length of the chain, and create branches on that smaller chain. So the shorter the chain and the more branched the chain, the lower the boiling point. And obviously then, the smaller and the more branched and the lower the boiling point, the more useful that particular hydrocarbon is. So therefore, we do use this process also of isomerization to take large, less useful hydrocarbons and turn them into smaller, more useful hydrocarbons to satisfy the demand of humanity for hydrocarbons as a fuel. I did mention down here that you only need to be able to draw and name the isomers of C4H10 and C5H12. Now, I hate this you only need to do, okay? You should be able to draw isomers of anything up as far as octane. Now, octane is fun because there are 18 different isomers, which I'm going to leave you with as a puzzle. But C4H10, MEPB, butane, and C5H12, pentane. They are the ones that will come up simply for time. You don't have time to write out 18 isomers of octane, for example, in a state exam. So for the purposes of the exam, they limit themselves to C4H10 and C5H12. However, I would expect you to be able to do the isomers of anything, of any of our hydrocarbons up as far as octane. Okay, so just keep that in mind. When we talk about isomerization, there are three different types. Okay, there's three different types that we can change the structure of a molecule to give us a new compound by using the same number of atoms. One is by making changes on the chain itself. So if you take a chain of 8 and maybe you remove a CH2 unit, push the ends together, then you're down to a chain of 7. But you can move that CH2 unit around each of the remaining carbons to see if you get a new name and a new structural formula. So if you get a new structural formula, then you have a new molecule, which is a new hydrocarbon, probably a more useful one. So the chain is where we snap off little bits and we move them around the chain to see what names we get. The one thing to remember is that if we go from, say, from pentane into 2-methylbutane, well then the new name would suggest that we have slightly different physical properties and obviously then a lower boiling point. And that's all I'm saying here, is that when you do rearrange the carbon skeleton, you will have similar chemical properties, you'll have slightly different physical properties because it's a different substance, and then you will have a lower boiling point. And that's the aim of an organic chemist, to take something that's long and less useful and isomerize it into something smaller and more useful. So that's the chain. So we could change the chain's length and move the little bits that we have removed around it. The second one is a positional isomer, where we take the double bond, or indeed the triple bond, but we won't be dealing with alkynes, but we move the double bond between the different carbons in order to see, does that affect the name of the molecule? And if it gives me a new name, then you have a new molecular formula, same molecular formula, a different structural formula. So you have an isomer, okay? And the last one, which we'll kind of look at maybe towards the end, maybe sixth year, is where we have a functional group difference. Now, that means that you would, for the example, the functional group of the alcohols is OH. So you could actually take that functional group and you can move the functional group itself around the carbon skeleton. So there are three types of isomerization. The chain, where we break off parts of the carbon skeleton and move it around the place. We make a change on the carbon skeleton. The positional, where we make a change with the actual moving the functional group, so moving the double bond around different carbons, okay? And then the functional group is where we actually take, say, the OH of the alcohol, move that around the carbon skeleton and see if we get a new name. Therefore, we'll have a different structural formula and a new isomer. Okay, so here's an example. We'll just do an example very quickly with butane. The one thing I want you to remember is this, that any time they ask you to write out the isomers of a given hydrocarbon, the very first isomer is always just the molecule itself. So if I asked you, what are the isomers of butane? Well, the first isomer of butane is butane. So you would draw the molecule, as you can see down there bottom left, you draw the molecule as a straight chain of 4 carbons. And don't forget the ratio in an alkane is CnH2n plus 2. So therefore, there's 4 carbons, there would be 10 hydrogens. So keep that in mind. So that would be the first one. And then what we talked about was the chain isomer. So we're going to take a CH2 group here. So we're going to take this CH2 group here, and we're going to move that in here between this carbon and hydrogen. Now, how do we do that? How do we manipulate a carbon skeleton? The answer is we use catalysts. All right. So a specific catalyst would be used in order to make this 4 chain into a 3 chain with a branch. 4 chain, butane, into a 3 chain with a branch. The only one that's possible in relation to our carbon skeleton is 2-methyl propane. And 2-methyl propane would have a lower boiling point than butane. Okay, so this is one where we're changing the chain. And notice we still have the same number of atoms. So we still have 4 carbon atoms, we still have 10 hydrogen atoms, just arranged in a different structure. And because we have a different structure, we have a new name. And because we have a new name, we have an isomer. Okay, let's have a look. What difference does it make? Well, first of all, just take a look at the bottom of this slide here. You can read the rest yourselves later on. Butane, this one, has a boiling point of -0.5 degrees Celsius. But if I was to take off a CH2 group and move it in here between this carbon and this hydrogen, I'm going to get, as we said already, 2-methyl propane. And 2-methyl propane has a boiling point of -11.7 degrees. So 2-methyl propane. Okay, and that lowers the boiling point of that organic molecule. Taking an alkene. Now, if we take, for example, pentene, this is the one I talked about in terms of your double bond position. Okay, so we can take pentene, in this case here, pent-1-ene, and we can move the double bond from carbon 1 and 2 into the space between carbon 2 and 3. Now, do I get a new name? Well, we still have 5 in a row here, but now you'll notice that the double bond is firmly between carbon 2 and carbon 3. So this one here is pent-1-ene, whereas this one here is pent-2-ene. And if I was to move that double bond in here, you would think I would get pent-3-ene, but I don't, because I count from the other end, giving the double bond always the lowest possible value. So if I count from here, I get 1. If I count from here, I get 2. But if I move the double bond in here, I've got to count from the other side, which will still give pent-2-ene, same name, same structure, not a new isomer. So, what are the other isomers of pent-1-ene? Well, let's take a look. We know pent-2-ene is the first isomer. So there's the first isomer here. There's the second one. And down here it says that there are 3 other structural isomer with a chain of 4 carbons. So let's take a look. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. Let's see if we can find them. Okay. So what does it mean when we're taking a chain of 4 carbons? It means that we're removing one of these CH2 groups and we're going to start to move it around the place. So let's keep the double bond in the first position, and let's take this CH2 group here and let's put it there. Now, let's name this molecule. Well, MEPB, so this is bute, Double bond is between carbon 1 and 2, so it's but1-ene. And then we have a methyl group on carbon number 3. Now keep in mind that the double bond dictates the direction of counting. So if the double bond is here, then we're going to count this way for everything. You give the double bond the lowest value, everything else has to fall in behind that. So that's carbon 1, 2, 3. So we've got 3 methyl, but1-ene. Okay. If I was to take that double bond here between carbon 2 and 3 and leave the methyl group there, now what do I get? Well, counting this way, 1, 2, 3, 4. Counting this way, 1, 2, 3, 4. So this time I get but2-ene. So straight away we have a new name. Now what about the group? Is it 1, 2, 3 or is it 1, 2? Well, because the double bond is in the middle and it's 2 from either end, you now give the methyl group its smallest number. So we're going to count from this way, and this would be 2 methyl but2-ene. Okay, where's the last one? Well, let's try the following. If I have 4 in this chain here, 1, 2, 3 and 4, and I take the double bond and I put it again there. Let's see, 4 carbons, double bond here. What else could I get? If I put it back there, I'm going to end up again with pent2-ene, so I can't put it at the end. Plus 1 branch. Let's see. There. Yeah, I suppose take that double bond from here. Just takes me a minute to see it. Get rid of that. Okay, let's put the double bond here, back into the first position. And let's this time move the methyl group to here. Okay, now what have I got? This time MEPB, so I've got but, double bond, ene, after the first carbon, 1, and this time I have 2 methyl, but1-ene. So you got to play around with these things. They're tricky, they're nice puzzles, but this is what we do with isomerization. So they are the 3 isomers, 3 remaining isomers I should say, of pent-ene when we reduce the longest chain down to 4 and move the CH2 group around the place. Okay, so I'm going to leave you with this C5H12. Now you've got to check in your head first of all, is that an alkane? Is that an alkene? Well, what's the ratio between the carbons and the hydrogens? 5 is to 12. That's N is to 2N plus 2. So this is definitely an alkane. So you're going to be moving around with pentane, then you're going to be going down to butane, and then if you can, try and get down to propane. But I leave that for you to do. I'm going to take a look at this one here. I'm going to take a look at the structural isomers of C6H14 and see what we can do with this one. So draw and name all the structural isomers of C6H14. Now again, is this an alkane or an alkene? Well, what's the ratio between the carbons and hydrogens? 6 is to 14. 6N to 2N plus 2. So this is definitely an alkane. An alkane with 6 carbons happens to be hexane. So I want to get all the structural isomers of hexane, and that's exactly what I'm going to do. So, as I said to you first of all, the first isomer of hexane is hexane itself. So 1, 2, 3, 4, 5, and 6. So there's your first isomer. Okay. Now, what I'm going to do is I'm going to take a CH2 group for a walk around the other carbons. So let's break it down to 5. So you reduce the chain by 1 carbon, and you start to move the CH2 around. So if I put it here, what would that be? That would still be 6 in a row. Little kink at the end doesn't matter. Longest chain would still be 6, so we can't use that. But if I was to put it here, what would that be? 1, 2, 3, 4, 5 be pentane. But wouldn't it be, counting from this end, 2 methyl pentane? Okay, so there's your second isomer. All right, the next one, let's move it again. So 1, 2, 3, 4, 5, and let's move that CH2 group to there. What do I now have? Well, again, I still have pentane, but this time I have 3 methyl pentane. And as long as it's a new name, It's a new structural formula. It's an isomer. So as long as the name is new and name is different, then you have an isomer. It's only when you get the same name that you know you're repeating molecules from before. And they could be mirror images of a previous one that you've actually drawn. Okay, the next one. Now, if I move that one here, well, then I'm back to a mirror image of this one. So I've run out of options for this one. So what do I do now? Now I take off another CH2. So I reduce the chain down to 4. And I move 2 CH2s around the place. Now, if I was to put them here, if I was to put one there and one there, what would that give me? Longest chain is 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3. So longest chain here would be 4. So again, MEPB. So now we're dealing with butane. And what about it? Counting from the right to the left, you'll notice that there are 2 methyl groups on the second carbon. So this is 2,2 dimethyl butane. New name, new structural formula, new isomer. Okay, now let's take one of these onto this carbon. So stick with the 4, leave that methyl here, and let's take this methyl onto this carbon. Now do I have anything new? Well, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4. Longest branch is still 4, so that's still butane. Okay, but this time we have the methyl groups on carbon 2 and 3. So again, new name, slightly different from this one, new name. Similar chemical properties, slightly different physical properties, but we've got the same number of atoms. Excuse me. I'm doing so much talking these days, I'm beginning to lose my voice. So there we have them. 2,3 dimethyl butane. Now, is there any other option? Can I move these anywhere else? If I move that back here, then I re-establish the longest chain of 5 again, and that's no good to me. If I take the 2 of them together, I'm going to ask you a question. Is this a new isomer? So if I put an ethyl group here, do I have 2 ethyl butane? And the answer is no. Because if I put an ethyl group here, you think you have 2 ethyl butane, but in fact, what's the longest chain? The longest chain is 1, 2, 3, 4, 5. So we're going back to pentane with a methyl group on the 3rd carbon. So that would be 3 methyl pentane, which we already have up there. So again, check it, get the name by the IUPAC rules, and if you get the same name as a previous, then it's just a different structure of the same isomer that you had before. Sometimes a mirror image, sometimes just a slight structural change to the actual chain. So that means that is not an isomer, and the isomers we have therefore are 1, which is hexane itself, and don't forget, the first isomer of every molecule is the molecule itself. And then we've got the deviations. So we go from a chain of 6 down to a chain of 5. Play around with 1 methyl group until you run out of options. Then bring the chain down to 4. Play around with 2 methyl groups until you run out of options. And then see if you can get down to a chain of 3. But in this case here you couldn't, because no matter where we put them, we'd end up with something that we've already had before. So I'm going to leave you, as I said before, I'm going to leave you with C5H12. I'm going to leave you with C6H12. Now I've done C6H14, so I've done hexane, but I'm going to leave you with hexene. So just keep in mind, the way you know this is an alkene is the ratio between the carbons and the hydrogens. 6 is to 12, so therefore it's CnH2n, and that's an alkene. Okay, so that's the only thing I will tell you. It's an alkene, it's hexene. So you can play around to get the structural isomers of that one. You can then take C7H16 and have great fun, and then look at the worksheet that I've left you in Google Classroom. The worksheet that I've left you in Google Classroom is a worksheet that gives you a grid and asks you to find all 18 isomers of octane. So have fun with that one. That's a real daily puzzle. See if you can fill out all 18 grids with the isomers of octane, and I'll give you the answers to that one in the next class.